All right, isomerism. You have probably done this in school. You've definitely come across this word in grade 10. What do you know about isomerism, or what is your understanding of it? How much do you know about it?
I know that they have the same like formula, but it's just that like some of the properties between them are different. Even though the
Awesome.
formula.
Hey, you're close, pretty close. You have the right idea.
Same chemical formula, but different molecular structure.
Absolutely. That is 100% right. That's what isomerism is. Slight modification, I would say, same molecular formula. Okay. So if you take one molecule of it and just count what all atoms are there, they would have the exact same atoms, same number of atoms also. So let's say the same molecular formula. But different structures, or in other words, you can also say different structural formulas. And if structure is different, of course, like all the properties also will be different.
And I have a doubt.
Yeah.
The molecular formula of organic compounds, like it's so like specific to the structure, like where what is attached. So how could it have the same molecular formula with different structures?
Ritu, structural formula is the one you're talking about. Molecular formula is just saying like yeah, we'll be discussing some examples. Yeah, it'll get clearer. Take these two structures. Okay, we'll start the simplest one: CH3, CH2, CH2, CH3. So this is butane. Butane का molecular formula क्या है?
C4H10.
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 Yeah. So this is what you call the molecular formula. So molecular formula just tells you what all atoms are there and how many of those are there. Writing the structure, like the one where you're showcasing the structure, so that's the structural formula. Where you have different ways of representing it. You have the condensed and you have the line-based things. Okay, so by contrast, so I'll present another compound. Look at this one, CH3, CH3, CH3. What is the name of this compound?
2-methyl propyl. Propane.
Propane. 2-methyl propane. Now, इसका molecular formula क्या है? Count the number of atoms. Tell me.
C4H10.
C4H10. Yeah. So this is what is a situation. Like, think of it as, you know, let's say you have a cup full of Lego bricks. Now you can use the same Legos to build like so many different structures, right? So this is also just like that. You have 4 carbon atoms and 10 hydrogen atoms. This is one way to arrange them, where you get butane. And this is another way to arrange them, where you get 2-methyl propane. But the building blocks that you used are the same. Like both have the same molecular formula, which is C4H10, both the cases. Okay. So this is what isomerism is. Molecular formula is this. Like it is something that tells you nothing about the compound. It tells you only how many, like what all atoms are there, like carbon, hydrogen, oxygen, maybe nitrogen. And then it tells you how many of the atoms are there. It doesn't tell you anything else. So this is what is called the molecular formula. And where you write it in an expanded form, where you display the structure. That's the, basically this is the structure. You can see that there is a difference in the structure, and so their IUPAC names are also going to be different, but the molecular formula is the same in both the cases. Yeah, that is what isomerism is. So does that clarify, Ritu?
Yes, ma'am.
All right. So you guys do have like a basic idea of isomerism. Now, like you guys know what it is and all. Okay. Now, difference in structure, matlab, there may be so many, like that difference can come from so many places. Okay. So based on that, you have different types of isomerism. All right. Roughly, isomerism is divided into two broad types. So if you have isomerism, either you can have completely different structures itself, like just a whole lot of difference in the structure, in which case that's a structural isomerism. And or the overall placement of the atoms, like the arrangement of the atoms may be the same, but the orientation may be different. So that is called geometrical isomerism. So we will be getting into both of these types in detail right now. So don't worry about it, you'll get clearer. But overall, like, why do we have differences? One is structural isomerism, where the structure itself is like outright different. Geometrical isomerism, the structure is more or less the same, in the sense that if you see, okay, यहाँ पे 3 carbon atom का chain hai, and you know there is OH attached over here and CH3 attached over here. So that way you have a rough idea of, you know, what is the structure. Like they're pretty much the same, but the spatial arrangement, like 3D geometry, like if you compare both the 3D structures of it, the orientation or the spatial, like where exactly is it? Like, is it angled this way or this way? That sort of a difference will come up. You know, that is what is geometrical isomerism. So we will be doing each one and we'll take lots of examples. So it'll be quite clear to you guys. By the end of this class, it'll be quite clear. That I can tell. Within structural isomerism, so again, just talking about structure is a really broad term. There may be many differences within the structure itself. So the first type is called chain isomerism. All of these names are very, very self-explanatory, okay? Very easy, at least in structural isomerism. You have chain, then you have position, then you have functional group isomerism, and finally you have something called metamerism. And within geometrical isomerism, you have, oh, I'm sorry, like called the stereo isomerism. Geometrical is one type of stereo isomerism. Isme you have geometrical and optical. So as a whole, this is basically called stereo isomerism. So be a little familiar with this word stereo. So stereochemistry deals with spatial arrangement of atoms. Stereoisomerism is spatial arrangement, or you know, like orientation may agar difference hai, so that's why it's stereoisomerism. Like some reactions, you know, like some reactions, why they don't take place or something, you'll come across words like It's because of steric hindrance or stereochemistry. So whenever you come across the word stereo, it just means that it has to deal with how the atoms are organized in space. Like, are they tightly bunched together, or is there a lot of space between them? Basically, it has to do with the arrangement or orientation of the atoms in the molecule related to that. Okay, so that's stereoisomerism. Isme you have two types. One is geometrical isomerism, and another is optical isomerism. The fancy word that you use for optical isomerism is enantiomers. Okay, so let me know once you've noted this down. Then we'll be looking at each one of this one by one. So 6 types, 4 here and 2 over here. Okay, Adit is done. Arnav is done. Okay, Smira done. Ritu is also done. Okay. Ritu, question or you? Okay. The first one we'll be looking at within structural is chain isomerism. Again, if you guys already have an idea about it, if you are able to figure it out, definitely do stop me and answer. Like, don't be quiet. Take a random guess. What do you think chain isomerism is? Like, you know what is isomerism? And this type is chain isomerism. So what could it mean? You want to take a random guess?
Are there like different chains attached to one principal chain?
No, I don't understand what you're saying, Ritu. Different chains attached, matlab?
Like instead of being like if you had the C4H10, like you had given us the example of the methyl propane, like that sort of thing.
Yeah. In that sense, yeah. Adit, what is your answer? I see you raised your hand.
Like many compounds can have like this, like how isomerism says that it has the same like molecular formula, but I guess here it's like the structure is chain, I guess. I don't know.
Yeah. So the difference is in the chain length. Okay. So it's chain isomerism when the difference is in the chain length, the parent chain length, you can say. Okay. So if you have to put it in words, so difference in structure bol rahe na? Which specific way is the structure differing in? If there is a difference in the parent chain length, so that's chain isomerism. And as Ritu said, like the butane and 2-methyl propane may, you could see that it was pretty obvious. You had CH3, CH2, CH2, CH3 versus CH3, CH2, CH3. So both have the molecular formula C4H10, but यहाँ पे the chain length is 4 carbon atoms, and यहाँ पे the chain length is 3 carbon atoms, right? That's why you can see the difference in IUPAC name also. This is butane, and this is 2-methyl propane. So wherever you find chain isomerism, there is an obvious difference in the IUPAC name in the parent name itself. Yeah, यहाँ पे butane है, यहाँ पे propane, because there is a difference in the parent chain length. So related to chain isomerism, Iska common name, like IUPAC name is 2-methyl propane. This is also called isobutane. Logic, you can think of it as, this is an isomer of butane. That's why it's called isobutane. Okay. So this is example 1. Another example is, look at pentane. Like all the isomers you can form with C5H12. So the first isomer is pretty obvious. Draw the straight chain. 5 carbons, lay them out side by side in a straight chain. Then second isomer, take 1 carbon atom, put it somewhere in the middle of the chain. And another one, take another one and put it in the middle of the chain. So this is what you get. Okay. Can you get any more isomers from pentane? Yes, no?
Yes.
You could have one where you attach like an ethyl group to 3 carbons.
Wait, what do you want me to do?
You could have like an ethyl group attached to 3 carbon chain, like the parent chain.
How many carbon long is the parent chain?
3 carbons long.
And where do you want to attach the ethyl group?
The second one,
Okay. All right. Iska IUPAC, like give me the IUPAC name for all 4 of them.
First one is pentane.
second one is 2-methyl butane.
Okay.
Third one will be 2,
2
1 second.
dimethyl propane.
2, 2 dimethyl and propane.
Dimethyl propane.
The fourth one is 2-ethyl propane.
Is Ritu correct?
No, it's 2-methyl butane only. It's similar to the second one.
Got it, Ritu?
Ma'am, are the second and the fourth one same then?
Yeah, longest chain rule.
So they are the same then, okay.
Yes. Okay. So that's another advantage of IUPAC names. Because you have like certain set of rules describing the name and all, it will get rid of these sort of confusions. So if you're wondering if this is like a different isomer or same isomer, ho sakta hai kya? Simple test is write down the IUPAC name for it. So if the IUPAC name is the exact same thing, फिर compound same ही है. If there is a difference in the IUPAC name, then it's a different compound. But yeah, you need to make sure that you don't make mistakes in figuring out the IUPAC name. Okay. Yeah, that what's up?
Ma'am, for the second and the third one, the 2-methyl butane and these are not the IUPAC names, right?
These are the
Or
IUPAC names. Like we followed those rules, no? Longest chain, then substituent and position, like the numbering of the substituent. So these are IUPAC names.
Okay.
So the common names for this, so whenever something is in a straight chain, you call this N-pentane. where I wrote N-pentane, is that visible or is that like too much niche?
Oh, it's visible.
Visible.
Visible, right? Okay, agar koi problem hai to bata do, then I'll write it somewhere else. Now, this particular thing, so this is called isopentane. And this is called neopentane. So these prefixes, iso and neo, wherever you use it, N, iso and neo, these are basically common names. And this sort of naming only works with butane and pentane, because if you start having greater number of carbon atoms, then the number of isomers is also going to, you're going to have butane mein you have 2 isomers, pentane mein you had 3 possibilities. Hexane mein I think you can go up to 5 possibilities, 4 different isomers I think. And then heptane, octane, like if you increase the number of carbons in a molecule, the number of isomers increases exponentially. So giving it a common name to every single isomer defeats the purpose. So this iso-neo funda, like you will find only for butane and pentane. I have not come across any other neo molecule, possibly hexane, like neohexane, but that also I've rarely ever heard it. I don't know if I've heard it at all. Neopentane is the most common one. Iso, I've heard for isopentane and isobutane, isobutane being more common. N-butane, N-pentane, because N, so basically N stands for normal. So this is used for any hydrocarbon because it basically means that it's a straight chain. So if I say N-octane, it just means that you have to put like 8 carbon atoms beside each other and it's an alkane made up of that. 1, 2, 3, 4, 5, 6, 7. So this is N-octane. N-decane means, so the prefix N is the most commonly used for all alkanes. When you need to indicate that it is a straight chain compound, उसमें कोई branching नहीं है. Okay. So iso and neo are used for very specific situations. You use iso when you have this sort of a situation. When you have a when you have a tertiary carbon, I'd say. Okay, so when you have carbon attached to 3 other carbons, this sort of a thing. Here you have carbon attached to 3 other carbons. So this sort of a situation, when you get it, so that's iso. So another example is, this is something you must be really familiar with because it is a component of sanitizers. So when you come across isopropyl alcohol, so alcohol tells you that there is OH, iso tells you, propyl tells you that there's 3 carbon atoms. Iso tells you how those 3 carbon atoms are arranged. So it is basically C, C, and OH. So this is isopropyl alcohol. Okay. So iso is basically when you have carbon, like when you have basically a CH in the middle. Here you have CH in the middle. So that's like an iso thing. There's a T shape being formed with it. Okay. And neo is when you have 0 hydrogens attached to any carbon. Like you see that all 4 of it is attached to something or the other. When you have 0 hydrogens attached, that's a neo group. I've only seen neo being used in the case of pentane. N is the one that's like the most widely used. Okay. These are just like naming conventions. These are again common names. Yeah. Got it? Okay. Adit Arnav said yes.
Yes, ma'am.
Okay. So this is one like structures when you're figuring out the isomers. It is way too easy to, draw the same structure. You just like draw a mirror image of it or whatever. Like everybody, whoever is learning organic chemistry has been through it. So that is one thing that you need to look out for. Okay. All right. that was chain isomerism. You could see that the difference is in the basic length of the chain itself. Yeah, 5, 4, 3 carbon atoms. 4 carbon atoms, 3 carbon atoms. The next one is position isomerism. Anyone wants to take a guess कि ये क्या हो सकता है? In this case, the differences will be in किसमें होगा difference? Position isomerism.
The position.
Position.
Yes, position of what though? Think of organic compound molecules. Position.
Functional group.
Carbon.
The parent chain also is carbon, right? Like the whole structure itself is different. So carbon is really vague. Functional group is a good answer. Functional group is one. Let's use a generalized word for it, substituents. Okay, so substituents in the sense, this can be a functional group, as Adit said. This can be a random like alkyl branch also. Okay, so pretty easy. Like if you write down the IUPAC name and the difference that you get is in the prefix part of it, so that is position isomerism. So the most simple example that I can take is alcohols. Let's say CH3, CH2, CH2OH versus CH3, CHOH, CH3. So the molecular formula क्या होगा in both the cases? So 3 carbons, how many hydrogens are there?
8.
8. And oxygen?
1.
1.
Yeah. Okay. So the molecular formula in both the cases is C3H8O, but you can see that the structure varies here. What is the IUPAC name, Iska?
Propanol.
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 No, be a little more specific. The IUPAC name we're talking about.
1 propanol.
One
Propane, 1 all.
Absolutely, both are correct. 1 propanol you can say, or propane 1 all is also you can say. Both are correct. You're indicating the position of the all, which is the OH group. Okay, and the reason why is because look at like what would be the IUPAC name of this one?
Propane, 2
Propane
all.
2 all.
Propane 2 all, correct.
2 propanol.
2 propanol is also absolutely correct. You can see both of them are propanols, but the main difference is in this 1 versus 2. Okay, and this matters because when, like, if both of these undergo a reaction, the reactive site is the cornermost carbon over here, and the reactive site is the central carbon over here. So based on that, like for example, if I oxidize both of them, oxidation reaction agar kiya maine, this is going to produce an aldehyde, and then extra oxidation se carboxylic acid milega, purely because the OH is in the cornermost thing. But this is going to give me a ketone, which are 2 completely different compounds, right? So that is why the position of the functional group matters quite a lot. So that's why position isomerism is also important. Okay. What I meant, so this is an example where the position of the functional group itself is changing. It doesn't have to be just the functional group. It can be something like this also. For example, if I have CH3, CH2, CH, CH3, again CH, CH3, CH3 versus, let's say, CH3, CH2, C, CH3 twice, then CH2. Okay, are you guys familiar with this notation of representing organic compounds?
I've seen it once or twice, but not too much.
Okay,
I wouldn't say I'm like comfortable with this, but yeah, I've seen it before though.
you've seen it. Okay, like have you like maybe done questions related to this, or like have you understood it?
Yeah, in the questions that you gave us, there was like a few
yeah.
like this.
Yeah, there was some like this too, I saw.
Okay, so when something is in brackets, no, it just means that it's attached to the carbon previous to it. So we have to expand it. Its structure basically looks like this. यहाँ पे CH है. Because CH3 is in bracket, it means that it's attached to this CH. And then rest of the chain follows. CH and CH3 in bracket. So CH3 is over here and CH3. This translates to, यहाँ पे there's only carbon and then CH3 twice. So there are two methyl groups attached to this carbon. CH3, CH3, CH2, CH3. Yeah. So again, same drill. What would be the molecular formula for both of these? And give me the IUPAC name for both of these. Also, to start with, whenever you come across these sort of situations, right, highly encourage to just write down the structure in the notation where you're comfortable with it, be it just bond line or condensed or whatever it may be. So until it comes naturally to you, like when you're solving these questions, just write it down however you feel comfortable, figuring it out. Okay.
I'm so sorry, I made a mistake in the second one. I just realized.
Okay, cool. I was just about to ask. That's fine. I know what you meant, so it's okay. So what is the molecular formula for both of these? Just count, no? Like, or they have only carbon and hydrogen.
C7H16.
C7H16, it's coming. C7H16.
So both of these are isomers of heptane mainly. IUPAC name, yes. Ritu and Smira have already sent it. So this has two methyl groups substituted over here. So it would be 2,3 dimethyl. Dimethyl, that's why we're giving the position of both of them, 2, 3. And longest chain is pentane. In this case, the methyl groups are bonded to the same carbon atom. So this happens to be 3, 3 dimethyl pentane. So you can see here, just like with the alcohol, the base name is the same. Both of them are pentane. Chain length is the same. दोनों में dimethyl ही है. The only difference is in the position of the methyl group. So in one case it's 2, 3. In the other case it's 3, 3. So that is why this would be position isomerism. Arnav, I got your answer, Abhi. Adat also I got it. Good. Yeah. So when there is a difference in the position of substituents, the reason why I use the word substituent is because it can be anything that substitutes a hydrogen. So it could be an alkyl group, it could be a functional group, could be anything. So when it's the change is in the position of that group of atoms, then it's position isomerism. Okay. And yeah, so all of these are not exclusive to each other. You can have chain isomerism and position isomerism present in a compound. Okay, so for example, if the chain length is changing and the position of, let's say, the nitro group is changing, then you have chain isomerism and position isomerism in that particular compound. So it's not like all the 4 types are not exclusive to each other. There may be overlaps also depending on the situation. Okay. All right. Next, what is the third type? Functional group isomerism.
Functionalizing.
Functional group isomerism.
So what is the difference in this?
Difference in functional groups, like they are different functional groups.
Absolutely. The main rule for isomerism is molecular formula same hona chahiye. Structure, basically how that molecule is constructed with the same number of atoms, is different. So when the difference is in the functional group, it's a functional group isomerism. Can you think of any examples where you may find this?
Can I try?
Yeah.
I have a good answer for this. Okay. So you have one where you have like a ketone and alcohol, and the second one you have like carboxylic acid.
Interesting. That's a very good track you've taken, Ritu, but test it out. Okay. It may or may not be correct. Let's take ketone versus alcohol. Okay. Now, the number of atoms should be the same. Ketone alcohol there's only like 1 oxygen atom, so that makes sense. Let's look at the simplest ones. The simplest ketone is acetone, which is CH3, C double bond O, CH3. So if you were to construct an alcohol with the same number of atoms, तो कौन सा alcohol करना पड़ेगा? इसका आइसोमर क्या हो सकता है?
Propanol.
प्रोपेनॉल, ठीक है. What is the molecular formula in this case? You have CHO. How many C, how many H, how many O?
C3H6 and then 1 O.
Okay, इसका molecular formula?
Yeah, it's not the same.
C3H.
Oh, so 8 like number of hydrogen atoms में difference आ गया ना? So ketone versus alcohol नहीं, but you got it very nicely, Ritu. Slight difference, you will find functional group isomerism where the number of molecules are also exact same. These pairs are like pretty much fixed. Look at ketone versus aldehyde. Simple reason, right? Ketone or aldehyde में you have the C double bond O. Alcohol में you have C single bond OH. So of course there's going to be extra hydrogens here, double bond versus single bond. So that's why ketone alcohol or aldehyde alcohol will not be isomers. So think of it in those lines. So on those lines, ketone and aldehydes are functional isomers of each other of same number of carbon atoms. Similarly, alcohol के साथ क्या हो सकता है? Alcohol and what other functional group would be functional isomers? You need to see structures kisme similar hai. So you can like flip back to the what you had noted down yesterday and compare the structures.
Ethers?
There you go. Alcohols and ethers are functional isomers of each other. Absolutely right. Carboxylic acid and esters are functional group isomers of each other. Both have that COO part of it common. So these are like the most simplest and direct ones. Apart from this, you may also have like consider amide and an amino acid. So both have this C double bond O part of it. Oh no, this won't be because amino acid may there'll be an extra OH. So never mind, not this. But taking that forward, you can think of something like an amide plus a compound like, so amide may the C double bond O and NH2 are together. You can have something where you have C double bond O and then a few carbons later, yahan pe NH2 ho sakta hai. So then there is a functional group ka difference itself. So this sort of a case. Like you'll have lots of pairs where the difference is in the functional group, but if you have to think up examples, these are like the most straightforward go-to examples. So example 1, if you compare ketone aldehyde, just need to make sure that the number of carbon atoms is the same. And you don't have to like think twice, count the number of hydrogens and all that. Ketone aldehyde, only the placement of the C double bond O changes. So agar corner में है तो वो aldehyde बन जाएगा, center में है तो it's a ketone. So they will automatically be isomers of each other. And similarly, alcohol ethers also, it's just the placement of oxygen. So if it is in the center, then it's an ether. But if it's in the corner, then it becomes an alcohol. Same thing with carboxylic acids and esters. The structure is the same, just the placement of that varies, which is why they are completely different from each other. So CH3, yeah.
This is like when there's one oxygen. What if like there's 4 or 5?
Absolutely, like it depends on what functional groups, like again, you need to compare what functional groups are there. So if all of them are ketones, just that the placement of that carbonyl group C double bond O is changing, then it's going to be a position isomer. But एक में ketone है, एक में aldehyde है, or if it's like an enol situation, so that's again tautomerism. So that's a completely different thing. But yeah, like if the functional group itself is different, then it's functional isomerism. No, like again, to figure out what isomerism is there, you need to look at the pair of compounds individually. But considering like from an examination point of view, if you had to give examples on your own, have these go-to things in your kit so that you're not like left thinking in the examination room. Oh, kya karna hai? What should I do? What should I do? And in the options also, instead of checking each and every option, if you spot that, ek option mein there's alcohol and ether, all you have to do is ensure that they have the same number of carbon atoms and you can blindly put them as functional group isomers. Because hydrogens will automatically match up. The basic idea is that there should be a difference in the functional group itself. So if you want to compare IUPAC names, then the suffix part of it will be different. So you have dimethyl ether versus ethanol. So dimethyl है, eth है, ether है, OL है. Or you can look at this one. This is propanone, and this thing is propanol. Now both of them start with prop, but the difference is, this ends with ONE, this ends with AL. That is because the functional group is different. Everything else is the same number of carbon atoms and everything. Only the functional group is different. So these are functional isomers. That's another way of identifying. Let me know when you guys have noted it down. Go through it. Once all of this is clear, we'll go to the next one. Adit is done. Smera, Ritu, Arnav, just let me know when it's done. Arnav is also done. Swara, yeah, I saw that you're done. Ritu, just let me know when you're done, okay?
I'm on the last example.
Okay, cool. Which is the final one? Oh, metamerism. Okay. Do you guys have any idea what metamerism is? Like in case you've done it in school or something like that? Any idea, or is this like completely new? No idea. So unfortunately, this is not something you can figure out from the name. This is also like a very special type of isomerism. So this occurs only in specific functional group. It occurs only in very specific situations. Okay. So mainly you will find this sort of isomerism in ketones and ethers. These types of functional groups. Okay. So metamerism is basically when there is a different, or like when, so basically the difference in this situation, like difference in structure, is in the number of carbon atoms that are there on both sides of the functional group. So the difference is in the number of carbon atoms on both sides of the functional group. So because it depends on like both sides of the functional group, you can see it occurs only in functional group that occur in the middle of the chain, like ketones and ethers. Okay. So for example, I can give you one example. Consider diethyl ether. So CH3, CH2, O. Ritu, like look at the example, it get clear. Like it'll be better. Words means it's a little difficult to put it in words. With an example, it gets easier to understand. This and this. Okay. What is the molecular formula in both these compounds? Can you count and tell me what you get?
C4H10O.
C4H10O. In both the cases?
Was one.
Yeah. Okay. What is the functional group in both the compounds? Like identify the functional group, both the cases.
Ether.
Smera says ether. Is she right?
I think it can be. I think she's right. ROR, like the R is the compound. It's reacting.
Like oxygen attached directly to two carbons on both sides. So that is ether. So both of them are ethers only. So where is the difference in structure, or is there no difference in the structure between both? It's like spot the difference, guys. Like दोनों में difference क्या है?
Oh, वैसे if that's the case, then in the first one though it will be an ethyl, like in the both sides.
Yeah, both sides of.
And then the other one, whereas it has propyl.
हाँ, एक side
Propyl and methyl.
एक side methyl है, right? So whenever एक functional group है center में, you can see that the functional group is ether, oxygen, ROR. The difference is in the number of carbon atoms on either side of the functional group. So in case one, it is 2 plus 2. In the other case, it is 3 plus 1. So molecular formula is the same, but structures are different. Like functional group is also the same. It's the structures that are different. So you can think of it as a case of chain isomerism only. But it goes one step beyond chain isomerism because substituent may be different. In this case, there is methoxypropane, it is ethoxyethane. So again, it's a very weird case. It's like, oh, it could be a part of this, could be a part of this. And it's like a special case of isomerism. That's why it gets a different name called metamerism. And my bad, guys, I said ketones. If this sort of a situation happens in ketones, it becomes position isomerism because carbonyl compound or carbonyl group ka position is different. Esters and ethers mein hota hai. Okay. So I'll give another example also relating to ester. Same thing. So let's say you have CH3C double bond O, CH2, CH3. Again, you just have to change this side how many carbon atoms are there and this side how many carbon atoms are there. That's the only difference that happens in metamerism. So the C double bond O part will remain the same. You just play around with, take some carbon atoms away from here and put it over here. I can change it as HCOO. So I'll take the only carbon atom that's over here. I can put it over here. This becomes C3H7. So again, you can see that यहाँ पे there is an ethyl group, but यहाँ पे there is a methyl. यहाँ पे another ethyl group, but this has become propyl. Something that was 2 and 2 on either side of the functional group has changed into 1 and 3. So this sort of isomerism, where it's the difference is in the number of carbon atoms that you have, that sort of isomerism is called metamerism. Okay. Cool. Adit, I saw you did a thumbs up and raised your hand. Do you have a question? Or
I have a question.
yeah.
I didn't understand like what's the difference between chain isomerism and metamerism. Like you were saying, it had also to do something with the functional groups also.
Huh.
I didn't
So chain isomerism tells us that difference is in the chain. So chain isomerism can occur in alcohols, aldehydes, like that's much more encompassing. Like as long as the parent chain ka length difference hai, it's going to be chain isomerism. Now, metamerism has to do with functional groups that are there in the middle of the chain, like ethers and esters. Like ethers occur only in the middle. Like there are carbon atoms, like there are chains of carbon on left side and right side. Right? Now you can see that like if you had to figure out the IUPAC name for these two compounds, let's start there. Figure out the IUPAC name दोनों का. We discussed ethers को कैसे name करना है. So go back to it, refer to it. If you have doubts, like we'll work it out together, but try to give the name for both of these.
ethers don't have suffixes, right?
No, ends with normal alkane only. The thing with ethers is they occur as prefixes. There's an oxy attached to the prefix. So ether, I'll give a hint here. Their name looks like alkoxy alkanes, where this is the longer chain and the alkoxy part is applied to the shorter chain. Okay, now figure out the names for both of these. Oh, Smera has sent it here. Awesome. Rest of you also giving it a try?
Oh yes, ma'am.
Nice. Ritu also got it. Adit, Arnav, you guys sending?
Yes, ma'am, this time.
Ma'am, of which this thing?
Oh, you just reconnected, no? You had gotten disconnected. So यहाँ पे जो, like there are two ethers, right? Give the IUPAC name for both of these.
Okay.
Adit, you have confused yourself. 3, 1 are all like position numbers, right? यहाँ पे ether मतलब there is, you don't have to mention the position numbers at all. Also, dimethoxy matlab, do you find there are 2 methoxy groups? Are there 2 methyls attached to the oxygen? You're thinking too much, Adit. Like, simplify it. So ether mein there's oxygen and 2 sides to it, right? So check the number of carbon atoms on both the sides. So on one side, like whichever is the longer side, keep it as it is. Keep it as alkane only. So यहाँ पे 2, 2 doesn't matter. So the second part of it is just ethane for this. In this case, 3 is the longer side, so this will end with propane. Next, the shorter side will change into alkoxy. So the shorter side, again, 2, 2 doesn't matter. So you already covered ethane. So the only thing that is left is ethoxy. So this is ethoxy ethane. And this propane we already covered. So the only thing that's left is 1 carbon atom chain. So that's going to change into methoxy. So this is methoxypropane. That's it. No complication.
Miss, can you explain again? I
Simple.
didn't.
So like ethers ka name takes the form alkoxyalkane. So whichever is the longer chain, it remains as alkane. So basically, if you look at an ether, oxygen ke idhar udhar carbon chains rahenge. So count how many carbons are there. Like in this case, 2 carbons on left side, 2 carbons on right side. Equal number ho gaya, doesn't matter. Like they both will take. Like you can choose any of them. In this case, एक side 3 है, एक side 1 carbon है. So longer side is 3. So that's going to remain as alkane. So in this case, it's propane. In this case, it's ethane. Now look at the remaining chain. So ethane, ये 2 carbon atom का cover कर लिया. So the remaining part is again 2 carbon atom chain. So the shorter side turns into alkoxy. In this case, it is ethoxy. In this case, 3 carbons का हमने cover कर लिया, that became propane. So the remaining one over here is just the methyl group, like 1 carbon atom long thing. So that turns into methoxy.
Okay, ma'am. Thank you.
Yeah. So Adit, you have included alkoxy, alkane and all that. Like इसमें position numbers वो सब नहीं रहेगा. What you have done is, I'll tell you why it is wrong. Like you have mentioned 2,2-dimethoxy propane, right? So this will translate as propane, ठीक है. So I am drawing a 3 carbon atom long. 2,2 indicates that second carbon pe, so on this carbon, di, there's 2 of methoxy groups. So this is the structure I'll end up getting. So methoxy is OCH3 and yahan pe another OCH3. So this is what I end up getting from your name, Adit.
Oh, that's why.
So that's why, like that's the reason it doesn't make sense. Like just keep it simple. Alkoxy alkane. When the structure gets a little more complicated, then the name also gets a little more complicated. Okay. And 3,1-dipropoxymethane doesn't make sense because if you're talking about methane, there's only one carbon, CH3, CH2, whatever. There's only one carbon. So 3 and 1 का कोई question ही नहीं है इसमें. Okay. So just do a sanity check once you, once you figure out the name, right? Just do a sanity check कि सही है कि नहीं. Anyway, you can see it's ethoxyethane, methoxypropane. You can say that, okay, ethane, propane, like chain isomerism हो सकता है because number of carbon atoms is different. But also the methoxy and ethoxy, like the branches are also different, right? So that's what I meant by, using the comparison with chain isomerism. But metamerism occurs only in things where the functional group is in the center, like esters and ethers. And the basic thing is that there is a difference in the carbon chains on both sides of the functional group. So this is where you come across metamerism. Okay.
Do we do the second one also? Like the esters one?
No, let's focus on isomerism. Then we'll look at exclusively like questions related to nomenclature and isomerism. Yeah. Another point with this, like this type of isomerism is called metamerism, and the compounds themselves, they are called metamers. Like this pair is called metamers. Yeah. Generally, the compounds isomers bolte hain na. If those isomers specifically show this type of isomerism, we call them metamers. Just the name of this type. Let me know when you guys are done and we'll go to the next. So that's the end of structural isomerism. And we look at geometrical isomerism. So you want to go through it once, you can just revise it, see if you have understood it all properly. If not, we'll go over it once again. And yeah, let me know. Okay, so Adit, Ritu, Arnav, no. Cool, that's what we've done. Now we're looking at stereoisomerism. इसमें 2 types है. The first one we look at is geometrical isomerism. Have you guys done this in your school in class?
We are doing
Yes,
hydrocarbons.
ma'am.
Right
Oh,
now.
you already started hydrocarbons. Wow. It like just suddenly increased the speed. Okay. So what do you guys know of, or how much do you remember about geometrical isomerism? Guys?
This was like the one topic that I was like not sure of. That's why I wanted to do it from like square one.
Okay. No issues. That's what I want to know. अगर कुछ
That's
पता
what I have to do with like the shape or the geometry of the compound or whatever. I don't know.
correct. What other things do you know about it? Like, do you know any specifics?
When
No,
you say
because
the geometry, would this be like about hybridization?
No, the hybridization of the atoms is the same, but where the other bonded atoms are there, like that, the differences will be over there. Okay, I'll discuss this like properly then. Okay, we'll start from scratch. Geometrical isomerism. Oh, okay. I don't think it's like there in extreme detail in your textbook also, which is why you have all
we
this.
just skimmed through it in our school. They just like said it and then they went to the next topic.
Acha. Yeah, so even I won't be doing it in detail. I just want you to be familiar with the situation. कि ये भी होता है. I just don't want to give you the word and leave it at that. Okay. Geometrical isomerism, like stereoisomerism in general, both geometrical and optical, deal with the fact that the structure is the same. Like if you look at the skeleton, if you had to describe it, it's the same, but the orientation of it is different. Okay. So for example, geometrical isomerism, you can see it a lot in alkenes. I'm sure there are other places also, but most commonly, like the best example I can give you guys to make you understand is you need to look at alkenes. Okay. I'll take an example here. Alkene matlab, like what is the speciality of alkene?
Double bond.
It has a double bond.
bond.
Correct. So double bond hona chahiye. So if there is a double bond, what is the hybridization of each of these carbons here? Like, or tell me what shape this, like the molecule will take. Like if you focus on this particular carbon, how will the bonds be aligned or oriented?
You'll have like one sigma bond and one pi bond. So one along the axis and one that is above and below.
That is the double bond. What about the other atoms? Like, will they be like this? Or will they be like this? Like, what is the shape that you get out of like this structure? Like what is the shape?
Oh, like bent in that sense, like what shape?
Like how much angle, or will they be in the same plane? Like what would be the shape?
I'm not sure of the angle, but you made those V shape, those two lines. Like I've seen that before when we draw alkenes. So I'm gonna say that.
Yeah, you're saying that out of familiarity, but sp2, like okay, double bond banane ke liye, what hybridization does this carbon take?
sp2.
sp2.
Correct. And sp2 hybridization may, what is the angle that what is the bond angle in sp2 hybridization?
120.
120 degrees. Like that's where that V shape comes from. Because it's sp2, all of these are flat in the same plane and all these are aligned at 120 degrees. Okay. So when I ask this sort of a question, that's how you need to figure it out. It's not something far away. It's something you guys did before. Okay.
Okay, ma'am.
That's why, like when we were doing structure of atom and chemical bonding, I told you we will keep coming back to those two chapters a lot. Like every other chapter, we'll always come back to those two chapters. They are like the basics of chemistry. Because they are basically describing electrons kaise hote hain atoms or molecules mein. And chemistry is basically studying, where electrons are going and coming. And it's organic chemistry mein, it's specifically how electrons behave in carbon compounds. That's basically it. Okay, so just because the chapter is over, you've given exam, like don't leave it in the dark. Those two chapters you should always have at your fingertips. Okay. All right.
So the shape will be trigonal planar then.
Yes, trigonal planar. So forms a symmetrical triangle. So that's trigonal part of it. And they are all in the same plane. Okay, so that's an alkene ka structure. Now imagine if this was not a symmetrical alkene. So symmetrical matlab if you have the same atoms on all sides. Now I'm saying this is not symmetrical. So यहाँ पे एक H है, यहाँ पे Cl है. Now there are two ways I can put other two atoms over here. I can put H and Cl on the same side, or I can put it over here. Okay. Now you can see the molecular formula is the same, like 2 carbons, 2 hydrogens, 2 chlorines, 2 carbon, 2 hydrogen, 2 chlorine. The structure is also the same, like ये दोनों carbon double bond में है. There is a double bond here. 1 chlorine on each carbon and 1 hydrogen on each carbon. Same thing, 1 chlorine on each carbon, 1 hydrogen on each carbon. But will I get, okay, let's number this as 1 and 2. Will I get molecule 2 by doing anything with molecule 1? Doing anything in the sense, if I rotate it by 90 degrees or if I flip it, say 180 degrees. So by doing some sort of, like upar niche alignment, will I get molecule 2 from molecule 1?
Yes.
I don't think it will affect it even if you change the alignment.
Are they two, like, are you saying that both of them are the same? I'm gonna take samples. I'm gonna take some pens. Can you guys see the colors of these 4 pens clearly?
Yes, ma'am.
Yes, ma'am.
Okay, visible, right? Okay. So, no, but this won't work, no? I need 2 same, 2 different. Wait, let me change this. All right. So I've got blue and yellow pens. Okay, deal with this. So let's say yellow is hydrogen and blue is chlorine. Molecule 1, hydrogens are on the same side. So this is what the orientation is. Like beach mein carbon double bond carbon is the same, but you can see.
Yes, ma'am.
Molecule looks like. Clear?
Right.
Now, what should I do this in order? What should I do to this in order to get molecule 2? Like, if I make it like this, am I getting molecule 2?
No, you still won't get it.
If I do this, am I getting molecule 2?
No.
It won't matter. The alignment won't matter. You just have to switch the pens. Then I guess that's the only thing you can do.
Yeah, I have to switch the pens. Matlab, I have to break this bond,
We have hydrogen and then switch it.
and form another new bond, right?
Right.
Which means that are molecule 1 and 2 the same molecule, or are they different molecules?
Different molecules.
Different molecules.
They're
Different
different molecules, right? So that is the funda behind geometrical isomerism. So if you want to classify it as structural isomerism, they look like completely the same molecules. It's only the spatial arrangement that has changed. And I can't even rotate this, because if I rotate this double bond is going to break. So in essence, even though the molecular structure is the same, it's basically carbon Cl, like CH double bond CH and then Cl. Essentially, you can write the structure like this. But in reality, if you look at the 3D arrangement of these atoms, they're completely different. Like you don't get one out of the other unless you break the bond, and then breaking the bond matlab chemical reaction karna padega. So they are not equivalent. So this sort of a situation where structure is the same, but the spatial arrangement is different. The orientation of the atoms is different. So that is called geometrical isomerism. Okay, makes sense?
Yes, ma'am.
Understood?
Yes, ma'am.
Okay. Ritu, Arnav, better idea of it?
Yes, ma'am.
Makes more sense.
Okay, cool. Yeah, so these two are isomers. And again, IUPAC system may, once people recognize that, oh, this is another difference that's coming, and like this does matter in chemical reactions and all. So you will come across geometrical isomerism. It is explained more in detail, like why it matters and all of that in grade 12. There you come across optical isomerism. But yeah, so this is also sometimes called cis-trans isomerism. Or another notation that is used is EZ isomerism. Okay. So why these names is basically again coming from the structure only. So if you see here, hydrogen is on the same side here. Hydrogen is on opposite sides here. So when you have like the same atom on the same side, like where hydrogen is on the same side, chlorine is on the same side, this particular isomerism or this particular structure is called the cis structure, and this is called trans structure. And the names cis and trans are used as prefixes. So another example I can give you is you have cis-2-butene, and there's something called trans-2-butene. Okay, so cis means same side. So butene is basically 4 carbon atoms. So butene, if you see, you have CH double bond CH and then CH3 and CH3. So 2 butene hai, center mein there's a double bond. So cis-2-butene means the same atoms should be on the same side. So यहाँ पे this double bonded carbon is attached to a hydrogen and a methyl. Same thing here, hydrogen and a methyl. So cis के case में the hydrogens and the methyls are on the same side. Trans के case में they are on the opposite side. CH3, CH3, एक ऊपर एक नीचे, and hydrogens also on the opposite side. So that's the difference between cis and trans. And yeah, again, isomerism matlab different structures. You need a way to indicate the difference in those structures. And the way you do it in geometrical isomerism is by giving the notation of cis and trans. Okay. Another way is EZ. This is also used in IUPAC notation. Difference between cis-trans and EZ is, notice how you have chlorine and chlorine here. But instead of chlorine, if I use a CH3 over here, now it's not exactly the same atom, right? Like एक side chlorine hai, एक side CH3 hai. So when you have like different atoms on both the sides, then you use the notation of EZ. So then you look at the atomic number or atomic mass essentially. Atomic mass of hydrogen is 1, chlorine is 35.5, this is 6, and this is 1, right? So if the heavier atoms are on the same side, then it is, I think it is E, And when the heavier atoms are on the opposite sides, then it is Z. So EZ, its origin is German. They relate to German words, again meaning same side, opposite sides. Just the names are different. Cis trans applies when you have the same things. EZ applies when you have completely different atoms. And this is like the short note on geometrical isomerism. EZ ka, I'll just tell you guys what is E, what is Z. I'll just quickly confirm it. For me also it's confusing which is cis, which is same side, which is opposite. But you guys got an idea of what is like the funda behind it? Like, do you understand now? If someone's talking about geometrical isomerism, do you guys understand kya ho raha hai idhar?
Yeah, I understand it.
Okay,
Yes, ma'am.
good. Okay, cool. Oh, E isomer mein the higher priority groups are on either side of the CC bond. So it's the opposite basically. If there is cis, it's represented by the Z, and trans is basically E. Yeah, EZ is confusing for me because I could not figure out the logic to remember. But yeah, this is the idea. It's just different situations may different applications, but the idea is the same. Same groups on the same side, different groups on different sides. That's it. Okay. And the second type of stereoisomerism is optical isomerism. This also relates to, again, the spatial orientation. So this happens when you have, again, asymmetrical carbon. So let's say you have a carbon. Carbon forms 4 different bonds. Tetrahedral structure. You guys remember this notation, right? Like the wedge, the solid wedge, and the dotted.
View on the front view and the back view.
Correct. Yeah. So let's say it is surrounded by 4 different things. I'll use colors for easy understanding. Let's say यहाँ पे एक OH है, OHP black. Let's say chlorine is red. CH3 in green, and hydrogen in orange. So this is a completely asymmetrical carbon because चारों तरफ पूरा अलग-अलग substituents are there. Suppose there are 2 hydrogens, then it becomes symmetrical, then that will not show optical isomerism. Optical isomerism only happens when there are 4 completely different things on all sides. Okay. Now, this also is the same funda as the other thing. Take the mirror image of this. Imagine there's a mirror here. So, iska reflection kaise dikhega? The carbon atom in the center will be the same. And पीछे की तरफ ये इधर है, आगे की तरफ this bond. This will be the same. तो इसका रिफ्लेक्शन में ऊपर क्या रहेगा?
OH.
OH.
Then in the one towards the left, you will have the H.
Farther this thing is H.
And the one farther from it is the Cl, chlorine.
This
No,
side.
not that one, the other, yeah, the other side.
Cl over here, and over
The
here.
last one will have methyl.
Methyl. Again, 2D may it'll be hard to imagine. I want you guys, okay, let's bring the pens back. So I need black, red, yellow, and green. So I have black, yellow, red, green. Where are you? Here. Okay, let me get the 3D version of this thing. Yeah, OH black is on top, red is on the side. Instead of orange, I took yellow. So just adjust. So that is away from you. So it's over here. And green CH3 is towards you. Now, this is what you see on the left side. This is molecule 1. So this is molecule 1. Now, can you get molecule 2 out of molecule 1? Like, which way should I rotate this so that you get molecule 2? Chlorine has come on the opposite side, right? So let me just rotate it 180 degrees this way. So OH is on top, तो इसको constant रख लेते हैं. And this red part has come पीछे की तरफ, इस तरफ आ गया ना. So if I rotate it, okay, OH and Cl are in their positions. But what happened to the hydrogen and methyl? Did I get molecule 2 from this?
I'm actually a bit confused because it's like what you're showing is a mirror image, so I'm getting confused right now.
Oh, then direct me, however you think. Like whatever I show here should be the exact representation of what you see on the screen. So OH is on the top. Where should I put the chlorine? Molecule 1.
Ma'am, are you showing the first one or the second one right now?
First one.
Okay.
This
then.
which you are holding
it's
was the
proper.
second one. And
Oh, okay, तो फिर उसका reverse करना पड़ेगा. Okay, is the chlorine atom का placement exactly correct?
Yes.
Oh yes,
Yes.
yes. Now it's fine.
Okay. फिर hydrogen किधर है? Hydrogen पीछे की तरफ होना चाहिए. So the green will be आगे की तरफ, and hydrogen will be पीछे.
Right.
Now is it correct?
Yes, ma'am.
yes,
Yes, ma'am.
Okay. Now I have molecule 1 over here. Now what should I do to molecule 1 in order to get molecule 2 from it? How should I rotate it?
You can rotate it like 180.
Okay, hydrogen is on top, so I'll keep this constant rotating.
That will be constant. Like the OH will be constant.
So OH and
And now it's the second one.
is it the second one? Are the hydrogen and CH3 matching?
no, hydrogen and
No.
CH3 not matching.
Not matching, right? So basically,
Right.
if I take mirror image, again, these are not the same molecules. I have to like break bonds to rearrange them to get the same as molecule 1. So these kind of, so optical isomers, if you have to identify them, two main things. Point 1 is that you need to have an asymmetrical carbon. Asymmetrical is basically it's like you need to have a carbon which is attached to 4 completely different things. I took examples to make the difference clear, but it could be something as simple as methyl group here, ethyl group here, hydrogen here, and propyl group here. It could be anything. The only condition is that all 4 must be different from each other. So asymmetrical carbon. And the second thing is both the compounds should be mirror images of each other. Okay. So these two are optical isomers, and the special name given to these isomers, they are called enantiomers. So enantiomers, D-I-O-M-E-R-S. This phenomenon is called enantiomerism. So these are represented like they're called optical isomerism because again, the word optical is not random. They have a tendency to rotate light in different ways. So all those deeper details, we'll get into it in grade 12. Now, even if I told you guys, like you won't have a context for it, so it won't like make a lot of sense or it'll be easy to forget. So let's keep this aside for now. Yeah. So this carbon, usually this asymmetrical carbon is denoted, like if you look at books and if there's like an asterisk over any particular carbon, this is the reason why. So it is showcasing asymmetrical carbons. So it gives you information that, oh, this will show optical isomerism. And geometrical may, the way we had cis trans, optical isomers are denoted by D and L. Like there's a D isomer and there's an L isomer. So that's how you differentiate in IUPAC naming. Yeah. So do you get the idea of like stereoisomerism now? Like I hope it's not very fuzzy anymore. Like just know what they are for now.
I get it, like a little bit, like the basic thing.
I mean, I got what you're trying to say.
Cool. So as long as you guys understand why is it isomerism, like why are they not the same molecules, that is sufficient. That's the main thing. Yeah. Cool. The importance of this, so like there is a particular reaction, there's a nucleophilic substitution reaction that you will study about in grade 12. So there we'll go in like proper detail. And that's all there is to isomerism, guys. Uske baad reaction mechanisms and all of that. Awesome. So just a quick summary going back. So isomerism, the main thing is the same molecular formula, but the structures are different in some way. So now that we have studied all types of isomerisms, structure can be like, there can be a very obvious difference in the structure, like chain length is different hai. Where the atoms are attached itself is different, in which case you have structural isomerism, or it can be more subtle than this, like where they are attached is the same, but the orientation, like the geometry of it differs, in which case you get stereoisomers. So stereoisomerism, you have geometrical and optical. We saw the difference between both of those. Geometrical, remember, like alkenes are like the best example. Optical, when you have 4 different things attached to carbon. Structural isomerism, these are all fairly self-explanatory. Chain isomerism, you have difference in the chain lengths. Position isomerism, the position of the functional group differs. Functional group isomerism, the functional group itself is different, like alcohols versus ethers. Metamerism, if you have like a functional group, the like what is attached on both sides of the functional group, there is a difference. Okay, so that's like a quick summary of it. Right. You guys have a better idea about isomerism now?
Yes, ma'am.
Okay.
Yes, ma'am.
So now go back and solve questions related to it. So then you'll be like more confident about it. You'll feel better about it. It'll stick better in your brain. Okay. Right. So I think that about covers all of organic. Is there anything else you guys want to talk to me about? Like anything you want to discuss? Any part that I may have missed or something it was hard for you to follow, doubts, anything like that?
Ma'am, do we have acid derivatives as in like in this chapter that we have to do?
No, it's
Or
just
that-
for familiarity. Like if you look at like a table of functional groups and all, I saw them being mentioned. So just know what they are and that's it. Like know that they exist. Tomorrow, if there's any question that mentions acid and hydride, I don't want you guys to be completely blank about it. So just know that there are things that exist. You don't even have to know kahan se aaya hai, like to that extent. Just have a rough idea. Acid derivatives matlab, just have an understanding that they have C double bond O. यहाँ पे obviously alkyl group आएगा and this thing changes. So if it is OH, it's a straightforward acid. If it is NH2, it's an amide. If it's a halide, it's called an acyl halide. And if it is another acidic group like this, then this is an acid and nitrite. Like that, we just know that these cases exist. That's it. All right. Anything else? Have you guys revised the reaction mechanisms? Like what are electrophiles, nucleophiles, all of that stuff? Inductive effect.
Oh, ma'am, I have one
Yes,
more doubt.
ma'am.
In the flashcards that you sent yesterday, like about the 1 second, what
Yeah, let me open it over here. I'll display it.
yeah, like the order of priority.
Yeah.
So like what order is it like is it like sort of like it's increasing in the order or like decreasing in the order? Like what's the order here? Like
Oh.
it says like
Normal,
carboxyl.
I'll explain it. 1 second. Let me open that set. It's easier. Okay. So this is the order. So carboxylic acid takes the highest priority, followed by sulfonic acid, followed by ester. Acyl halides are also called acid halides. They're the same things. Then amide, then nitrile, then aldehyde, ketone. Like this is the general order. Okay. So this is applied like only in nomenclature. So suppose you have a compound that has a carboxylic acid, like there is a COOH, and I don't know, like, or yeah. And let's say a ketone.
So it's decreasing, right?
Yeah. So then
Okay.
you have to consider COH to be the highest priority because this is in the corner, this will always get 1. And yahan se calculate the chain length, 2, 3, 4. So your primary parent name, because this is priority 1, this will be butanoic acid. And this is treated as a functional group, like a substituent. Iska ek prefix ho jayega. Do you remember C double bond O ka prefix version kya hoga?
Also,
Oxo. So this will be 3-oxo-butanoic acid. Acid hai matlab this will always be 1, so you don't have to specify 1. Kyunki acid group kabhi chain ke middle nahi aayega. If at all it is there in the middle of the chain, you will always start off with the functional group. Like for example, if you had something like this, yahan pe COOH and yahan pe let's say a C double bond. Rest of it is all like filled up with hydrogens. Then longest chain should always include the highest priority functional group. So COH include hoga hi, like you can't ignore this. This will never be a prefix. So you start from here and then go with the longest chain. So it'll be 1, 2, 1, 2, 3, 4, 5. So then this is going to be 2-methyl 4-oxo pentanoic acid. Okay, because like 5 carbon atom acid to pentanoic acid. Then what all did you exclude? यहाँ पे एक methyl group है on the second carbon, and 4th position पे there is this double bond. So that's why 2-methyl 4-oxo. So that's why this order group. So carboxylic acid highest here. Even if you have something else, like let's take it from here only. Suppose you have an aldehyde and a ketone. Let's say you have CH3, C double bond O, CH2, CHO. Aldehyde is above ketone. So this will be the more important functional group. So your ending will be in Al, and then you'll start counting the chain from the aldehyde. So aldehyde will always get 1. Then this will be 2, 3, 4. So इसका नाम होगा again 3-oxo 4 carbon atom है तो butanol. So that's how you construct the name. That's what is the importance of this thing.
Oh, so that's how we like, use like the what number to be given so that we can make the name for the reaction or the compound.
It will help you decide. Like I can start numbering from here also, right? I can start 1, 2, 3, 4. Now, should I start from this side or this side? If I start from here, ketone will get the lower number. If I start from here, aldehyde will get the lower number. Now, because aldehyde is more important, I'm going to start my numbering from here. Like 1 will always go with the aldehyde, and then whatever number ketone gets, that's going to be the position number.
Oh, okay, understood. Thank
Yeah,
you.
that's the importance of it. Cool. All right, guys. Anything else that you want to discuss?
No, like what happens is I think I get it all, and then 1 or 2 days later I realize that I didn't understand it. So I have to.
I know, yeah, that it requires some digestion. Like that's why keep constantly revising. Like that's why do the questions. So do a quick revision of the theory today so that you have, like, it's not just me telling you, you guys are also studying on your own. That works better. Then after a couple of days, like tomorrow, do like 10 questions. Day after tomorrow, do another 10 questions. So keep, like, don't just shut it and leave it behind. Keep doing that continuously. Yeah, Adit, what's up?
Ma'am, in classification, like I don't think we've done alicyclic and aromatic compounds.
We've not done in the first class. Sabse pehle kya?
I mean, I know in the first class we had done the general introduction, like about the sigma and pi bonds, wala, like how it works here. And then we did the branch chain and or the structures, condensed chain that we did. And then uske baad, I think we had our exams. And then after that, we continued from the mechanisms then. You
Okay.
said then
Classification part nahi kiya pehle. Okay.
like the
Over it. We'll do that. No issues. Again, classification is just so you guys are familiar with the terms and the definitions that we use. So let's say organic chemistry is the set of organic compounds, is a set of like all of the carbon compounds. Now, these carbon compounds, you can, like, they are broadly divided into aliphatic or aromatic. Okay, so aromatic is pretty self-explanatory. Aromatic is whichever compounds give you an aroma. Like these compounds have some sort of smell. If you were to associate it with some things like carbon dioxide, methane, ethane, all of these, like, are you able to smell these gases?
We can smell methane, right? The rest no.
No. You can't smell methane. Methane is a colorless, odorless, tasteless gas.
So what is it in gas cylinders that we smell?
So gas cylinders may, along with natural gas, they add another compound. So that compound is called ethyl mercaptan. So this is the compound that gives you that typical gas smell. And the reason why they add it is the exact same reason. Like methane is highly flammable. It's very combustible, right? So a little bit of spark and then it catches fire. Now, if the regulator is not working properly, or if you have not shut the gas completely properly, and if the gas keeps leaking, now gas matlab you can't see, it doesn't have a color, it doesn't have an odor. Detection difficult ho jayega, right? So and that's why they add this compound so that you can detect it, and if there is a gas leak, you can take the necessary precautions. Okay, but that's an excellent example, Ritu. So, you know, the typical smell of gas. Another example is naphthalene. Do you guys know the smell of naphthalene?
Yes.
We use it for like matcha and all.
What about lemons and oranges?
Citrus fruits.
Oh, it's used to clean like the bathroom, make it more fresh.
What about urea? Urea is an organic compound. Do you guys know the smell of urea?
Smells like fertilizer, right?
It smells like urine, basically. Urea is a big component of urine, so they have the same smell. Yeah. So that's the main difference between aliphatic and aromatic. So there are organic compounds that smell, and then obviously urea is a special case. Esters are like a different case, but aromatic compounds, all the aromatic compounds, they always have a typical smell associated with them. And that smell is because of they have a closed ring structure and they have resonance associated with them. Okay, so aromatic compounds are compounds that have a closed ring structure plus resonance.
So benzene compounds?
Yes, benzene compounds, and not just benzene. You have benzene.
Aniline.
Is the simplest one. Like aniline, all of these are benzene derivatives. You get them from benzene. You attach other things to benzene. But you do have organic compounds that are not benzene, yet they do show resonance and all of that. Okay, so naphthalene is another example. Naphthalene is similar to benzene, except it has two rings. Single ring is benzene. If you have two rings, that's naphthalene. This is the structure of naphthalene. So if you go look at mothballs, put them under an electron microscope or whatever, observe the structure, this is what you'll see. Okay. Of course, like citric acid, all of those, they have slightly more complicated stuff. Second. Okay. So aromatic compounds, the basic thing is closed ring structure plus resonance. Aliphatic is opposite of that. Okay, so if there is no resonance, so that would be aliphatic compounds. There are another type of compounds which have like no resonance and no ring. So basically open chain structures. So these are the characteristics of aliphatic compounds. They are also called acyclic. Okay, and something between both of these, you have another type of compounds which are closed ring but no resonance. So they are called cyclic compounds. Cyclic and aromatic, so they have closed chains. So along with the closed chain, if there is like a resonance possible in it, then it comes under aromatic. So if it is simply a closed chain without resonance, then it is a cyclic compound. If there is no ring structure at all, if it is like open chain, then it is acyclic or aliphatic. So within cyclic, yeah, like aromatic is one part of it. If there is no resonance, like we'll do a better way of representing this case. I'm so sorry if you've already noted this down, but there is a better way of doing this classification. So let's say aliphatic and cyclic. So cyclic is basically you have a closed chain or ring structure. Now within cyclic, you have something called alicyclic and aromatic. Alicyclic is no resonance, and aromatic is if there is resonance. Within aromatic, remember there's like one is benzenoid, like benzene. Then you have non-benzenoid. And you have heterocyclic. Yeah, these are like the names, like basic names of everything. So examples of acyclic, any compound without a ring, acyclic, like your regular butane, propane, branched chains, open chain alcohols, alkyl halides, like all of these are acyclic or aliphatic compounds. Alicyclic they need to have a ring structure and no resonance. So examples of this, simple, cyclohexane, cyclopentene, or let's go with cyclohexene, cyclopropane, chlorocyclopropane. So as long as there is any ring structure but no scope of resonance at all, that's alicyclic. Could be multiple rings also for that matter. Like this. Anything. Aromatic is there is resonance as well as a ring structure. Benzenoid is anything that looks like is derived from benzene. So basically a 6-membered ring with a resonance. So benzene itself is a benzenoid structure. Phenol, aniline, anisole, toluene, xylene, like all of these are benzenoid aromatic compounds. Non-benzenoid is if you have resonance, but it is not a benzenoid structure. Like you don't have a 6-membered ring. So for example, let's say there is a 7-membered ring with a 5-membered ring here, alternating single and double bonds. Something like this. So this is a non-benzenoid because you don't find any benzene ring, yet you have like it's completely closed chain and there is resonance happening here. So this is a non-benzenoid structure. Heterocyclic is if you have an atom other than carbon in the ring. So furan is a popular structure. Just confirm this. Pyrrole, pyridine, furan, okay, all of them. Okay. So pyridine is one 6-membered ring, but one of them is nitrogen. You have a lone pair over here. There is a double bond here, here, and here. So this double bond again keeps shifting. So this is called pyridine. And there is lone pair also that gets in a reaction. Then you have furan. Furan is an oxygen-based ring. FURAN. These are like a couple of examples of heterocyclic aromatic compounds. Yeah, so this is like the main classification of it. You will need to know like the main things. You won't get too much into non-benzenoid heterocyclic. You're literally not going to touch them anymore. The main thing you will be studying in the subsequent chapters also is aliphatic. So you need to know the difference between aliphatic aromatic compounds. Alicyclic to some extent, they behave more or less same as aliphatic with some minor differences. So reactions wise, properties wise, they're very similar to aliphatic compounds. Just that, you know, the reactivity may differ, the stabilities may differ, but otherwise, yeah. Aromatic and aliphatic undergo very, very different types of reactions. So main difference you need to know is between aliphatic and aromatic. And it makes it easy because aromatic, you will study mainly only benzenoid compounds. You won't go out of benzenoid compounds at all. Yeah, I'm sorry. Yeah, today I like today's class went on longer than expected. We'll end soon. Okay. Cool. So once you guys are done with this, we'll end today's session. Go over the questions for sure, because that is the real test of if you have understood, how much you have understood, and all of those things. Because organic mate theory does not matter at all. Theory is just so you know what these words are and things like that. The main thing is in the application-based question. So go over the MCQs for sure. Okay. Yeah. Guys, yes, no?
Yes.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Any questions, doubts?
I think I got it.
Okay,
No, ma'am.
cool. All right. So if there's nothing else, can we end the session here?
Yeah.
Yes, ma'am.
Okay.